Hello, 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 testing. Okay, before we go into the new chapter, can we revise again what's the process of blowing up? Let's say we first blow out an affine space. Okay, so how do we blow out an affine space at the origin? Hi, Jingsen, how do we blow out an affine space at the origin? Huh? 听不到? Exceptional divisor. What's the zero set you consider? Or what's the important map? Where do you get your exceptional divisor? What's the important map? Sorry? Polynomial? Map. What's the zero set? What's the tilde thingy? What's a and tilde? Using a line, yeah? Yeah, the keyword is line. So how do you find the line? X1, Y0 minus S0, Y1. Okay, so what are the X's and what are the Y? What are the X's and what are the Y? What are the X's? Huh? What are the X's and what are the Y? So X are the coordinate for the affine space, and then Y are the coordinate for the projective space. Okay. Do you agree that by doing X naught Y1 minus X1 Y0, this if you fix a point X naught S1, then the Y0 Y1 is the line that represents S0 Y0. Do you agree? Huh? Why you agree? Oh, let's say. Okay. Why are they on the same line? Because if you play this equation around, you literally get that the ratio of two coordinates is the same. Okay, if their ratio is the same, meaning they are on the same line. Is it? Okay, because the gradient is the same. Okay. So for general AN, you need to do for arbitrary IJ. Okay, so you need to do for arbitrary IJ here. Okay. And sorry. Okay, so this is the set of this thing. Okay, is the A and tilde. Okay, at the origin. Okay, what property we proved yesterday? We spent an hour to prove. What's the property we have proven yesterday about this A and tilde here? I think there are four of them, right? What are they? You you forget, but you remember there are four of them. Larry, Huh? Yeah, you can look for it. What property we prove? A tilde is a graph. Okay, if you disregard the exceptional divisor, let's define E to be the pre-measure of 0. And then what's this pi here? Where pi is the projection map for an tilde to an. Okay, where an tilde live here? An tilde live in an cross. My n have to be at the top. Huh? And cross p n minus 1. Okay, and then if I remove this is this is the closure, right? Closure. No, sorry. It's the graph, right? It's just the graph. Graph of what? S. Okay. What's S doing here? You just send AN to PN minus 1. Meaning what? Literally just send your point to your line. Contain it. The line we consider here is a special line. They are line through the origin. Okay. So this just describe what we are constructing here. Okay. Does it make sense? Make sense or not? Okay, so this one will give us a pair of points. Okay, one pair is just point, and then the other pair is line. But yesterday we proved that to get this line right, it is equivalent to set it as using equivalent class of SI. Right, yesterday we proved this. Okay. So if you put E back, then if you put your E back, then this is the closure of the graph. Okay. Closure of the graph. Maybe I write like this. Okay. Okay, what else we prove? This guy is smooth. Okay. A tilde is smooth. A tilde is smooth. Is also irreducible. Okay. Smooth and irreducible. So why is it irreducible? We can cover it using open cover. Okay. So what kind of open cover we can put here? Huh? Can you write down what's this VI here? What's the VI here? What's the description of these VI? Right? Vice. Vice. Yeah. Okay. How do you set this zero set here? Is it no zero set? This is an open set. Okay. It's a complement of let's say zero set over inside. Right. Okay. So this is sometimes we call this a hyperplane. Hyperplane. Complement of hyperplane. So this part here actually is what we call the distinguished open set. Okay, and these form a basis. Last time we show it. If you wonder, last time I think we used this kind of notation, EXI. Yeah, last time we defined this notation here. So in particular, we proved that this is isomorphic to AN, right? Okay, so there's an isomorphism to AN here, which we call psi 0, psi I, sorry. Okay, what does this psi I do here? So basically, you take a coordinate. Okay, let's say your coordinate looks like 0, x1, or 2, xn minus 1. And then how about your line? Let's say your line looks like y0 by 1, y minus 1. Okay, so what do you remember actually? You are just remembering the xi coordinate, and then you divide all the y0 by yi. Okay, and then you discard yi component. Okay, check if you have the right dimension or not. So here we got n from where 1 n minus 1 plus 1 n. Okay. Right, and then we show that this is an isomorphism. We show that this is isomorphism, have an inverse. So meaning what we're doing here is we're actually using these affine cover here, right, to cover our AN filter. Okay. Okay, make sense? Okay. Okay. Anything else I miss? Anything else? Oh, one last thing about your exceptional divisor. So basically your exceptional divisor is 0 cross with P n minus. Is 0 cross the whole thing. Why? Because if you go back to this 0 set here, if you put 0 on your S's, what are the y that satisfy this equation? Everything. Okay, anything. Okay, so you get everything. Okay, so this is about blowing up AN to AN. But how about blowing up a subset of it? Yeah, let's say we want to blow up a subset of it. What happened? We want to blow out a subset of it. So what color should I use? Let's say I use white. Okay, if I just blow up a subset of AN here, what do I get? Okay, basically, since you can blow out the whole surface, right? Okay, you just look at the pre-image of X, okay, inside this tilde here. Okay, so you just look at the pre-image of X inside this tilde here. Okay, and similarly, you can define a E of X, okay, inside E here. Okay, look at the intersection there, okay, with the excitation divisor. And when I talk about these, you got image or not? Huh? You have image, still have the two-dimensional image. You must keep your two-dimensional image in your mind. Huh? So how we blow up the line here, okay? Yeah. So I shouldn't do this. So maybe like this. Then you have the line, the E. Okay. Yeah, must have this image. Huh? So when I talk about X inside the space here, maybe you think about a curve here. Okay, and then you see these curve, right, must lie on some line. Okay, so this determine their height. Okay. Okay. And then yeah, so you can talk about S tilde here. So we are not sure that whether it's smooth or not. Not sure. Okay, in principle, you need to check again whether it's smooth or not. Okay. I think it's still irreducible. Is it irreducible? And maybe not, maybe not. Sorry, maybe also not. Maybe also not. Later I show you some example. Maybe not also. Maybe not smooth also. Okay, so that's why yesterday we discussed the theorem on by Hironaka that we can keep on blowing up. Later we'll ask Chiwi to do one blow up for you. It's his master stuff. Maybe he can present his master. Ah? What? What? Master implode? What do you mean? Master blowing. Oh, master in blowing. Oh, okay, okay. Yeah. So later maybe I ask him to share one example with you how you continuously do blow up. Okay, and yeah, so one very interesting about this EX, right? Okay, yesterday we showed that if you look at the exceptional of X, it is 0 cross with the projective con. Okay, projective con of x. So last time, remember, after we blow up, right? After we blow up, so let's say this point here will pass through here. Okay, let's say we draw this. Okay, so then after you blow up, what we get is this, the projective coordinate for the intersection and the exceptional divisor actually is the tangent, is a tangent, is the gradient for the tangent line. Okay. So you can prove in general that it is also true. It is also true. And then yesterday we go pretty quickly on other kinds of blow up. Maybe it's worth to go through again. If you have a question, you can ask also. Okay. Right. So before that, we have these two statements also. If it is smooth, the projective con is just the projective tangent space. Because when a point is smooth, tangent con equals to its tangent space. Okay, this is what we mentioned last time. Okay, I put the whole proof inside the notes already. Okay, so you can try and check back. And then all points on exceptional divisor should be the smooth point of S tutor. Okay, so this X here. Okay, this statement here refer to when the 0 point is a smooth point, when the point you blow up is already smooth. After blowing up, so it's meaning what? Meaning the blowout won't change the smoothness. Okay. If the blowout change the smoothness, then a bit difficult. You become not smooth again, become smooth again, become not smooth again. Okay, right? Alternate. But blowing up assure you that if you are already a smooth curve, you blow it up, it's still smooth. Okay. And then after blowing up affine variety, we try to blow up projective varieties. Okay. Basically, you need to link it back to affine space. But we know how to cover projective space using affine space. Okay, so we will view the point that you want to blow up in an affine chart. Okay, we call it the affine chart for affine covering. Okay, we use the word chart. It's a bit similar to differential manifold, where you also use chart, where you do the local homeomorphism to Rn. Okay, so this is similar. So you are like performing a local isomorphism. Okay, in this class we care about invertible polynomial. Okay, it's an isomorphism. Okay, so then you will do similar construction. Again, send the point to the line contain it. Okay. Okay. Let me go through the construction. I will show you some examples. And then yesterday we mentioned about blowing up along the ideal. So we are inspired by how we blow up along a point. If we want to blow up along a few points, how do we do it? Okay. So we try to make an analogy here. So when we do points, what are we actually doing? You take a point and then you look at where which line the point live in, right? Okay. But if you look closely, actually those projection map, right, built up by the generators of the maximal ideal of 0. You are using these xi to form your pi. So similarly, if you have an ideal, right, you can look at the generators. So xi are the generators for your maximal ideal here. So for general ideal, don't care what kind of ideal, not necessarily radical. Okay? You just pick your generator, okay, and then form this kind of method. And look at the line, okay, that formed by these FIs on the image, okay. But yeah, and then you look at the graph of it. Okay, previously we look at the graph, right? I will look at the point, okay, plus its line contained it. So similarly here, you look at this point plus the line contain this image. Okay, and then one thing you need to show that actually is independent of choices of generators. Okay, so one thing you need to show that this is independent of generators, and then what? So it does depend on, so there's an example says that it does depend on ideal, okay, but not on generators. Okay. So if you change ideal, for example, you see these two ideal is a little bit different. Okay. But the point they contain actually is the same. It's the same actually. Okay, you just put an x square here. Okay. But one of them is still singular, the other one already smooth. Okay. So this is blowing once. Maybe you blow twice, it becomes smooth. Okay, and then right, and then you can similarly define same things. Okay, same thing here. Maybe there's one thing you want to take note here is let's say I want to blow up some closed subvariety here. Okay, what should we do here? Perhaps. So if you want to blow up a closed subvariety inside X, perhaps you need to see the radical of that defining. Okay, and then we also mentioned about blowing up quasi-projective variety here, but because quasi-projective variety are open subset, right? Okay, so far what we are blowing are closed. Okay, so how do we blow an open set here? Okay, instead we need to look at the closure first. Okay, we look at the closure and then we blow along this closure. Okay, we blow on this closure here. Okay, we blow along this closure. And then you will look at the intersection between the blow up with the original X cross P minus 1 here. Okay, so you blow up the closure and then you go back and look for your open set. Okay, does it make sense? Make sense or not? You know what's the relation between closure and the space? You just add more limit point. Okay, then you blow those limit point and the space already, and then you go back look for the original X. Does it make sense? Okay, you just go back and look for the original. Your blowout points will link that PM minus 1 for the Y coding. So you just take the intersections. Okay, and then so one theorem from Hironaka here. So he got a few medal, okay, from this result in 1970, but he proved it in 1964. So what he proved is if your field is a field of characteristic 0, and then your X is quasi-projective varieties, okay, so any open subset of projective varieties. Because last time we showed that almost all variety you can realize as this kind of variety, so it's very general. Then there exists a smooth quasi-projective variety S tilde such that and birational morphism pi from this S tilde to X such that pi induces the isomorphism between X tilde taking away the pi inverse of, I think shouldn't be smooth, right? This one it should be singular. This is singular. Okay, so if you look at the complement of a singular point, okay, you should have isomorphism between the smooth point. Okay, if X is projective, then X tilde is also projective. So how we do this is doing a finite sequence of blowing up. Okay, he used a finite sequence of blowing up to find this X tilde here. If you can do this, this is what we call a resolution of a singularity, where you resolve a singularity. You kind of remove the singularity. Does it make sense? Okay. Okay, so before we invite Chiwi, Chiwi maybe can get ready first. I show them some blow up samples. Okay, I collect a bunch of examples from books, so you can try and go through and then try and do the calculation yourself. Because they are from different books, right? Maybe they are using different notation. Okay, so hopefully you are not confused by their notation. Maybe I just show you some picture. Okay, let me show you some picture. Okay, for example, let's say this example here. Okay, so can you imagine, let's say we want to blow this zero set up. Okay, so this is a zero set of xy. So can you imagine what point vanishes under this ideal xy here? Either x0 or either y is 0. Okay, so this is the horizontal line and vertical. I mean horizontal axis and vertical axis. Okay, so after blow up, can you imagine what happens? This is a surface blow up, A2 blow up. So you should have the picture that we discussed in class. Okay, so can you imagine that these two lines get separated? Okay. The top line, the vertical line and the horizontal line have different gradient, right? So they have different height. But along the same line, they are on the same height. Okay, so after blowing up, you should imagine something like this. Okay, so you see, x direction, y direction. Okay, x direction, y direction. Okay, yeah, makes sense. Okay, okay. Right. So let's look at the other one. Let's say about this. Y equals to x squared. Okay, this is a very normal function you will see right in high school. Okay, so if you blow this thing up, what happened? You can see that this opposite points, right? They are not on the same point. Okay, they are not on the same line. Okay, but they are opposite, right? So the gradient is it negative to each other? Yeah, negative to each other. Okay, so how will you draw out the blow up? Okay, so you need to check out. You need to check which line then, which line these points live on. Okay, and then plot the height out. Okay, so this is the blowout you get. Okay, see, makes sense or not? Okay, so this Z is the PI direction. This is the height. Okay, the gradient of your line live on. This is the positive part, right? Okay, so you can see that whether in the positive part, the gradient of your line live on also getting positive. Okay, so getting large. And then on the other side, getting negative, more negative. Okay. So on the negative part, you go down. On the positive part, you go up. Okay, so this is the picture. Yeah. Maybe this picture is better. Maybe this two is better. Okay, you see, they rotate the orientation for you to see what happens. Okay, makes sense? But you see, after you blow out, actually, it's kind of the same graph, right? Oh, same graph. Okay, but in a higher dimension. Okay, kind of the same graph here. Let's see different examples. So about this examples here, this is quite similar to what we had just now. This is x squared minus y squared here. Okay, what's this two line here? This is a two line, huh? Yeah, x plus y and x minus y. This is also simple reduction, right? Okay, you will make a squared minus b squared equals to a plus b times a minus b. Okay, so these are the two lines here. Okay, so you should imagine it's the similar blowout we get from just now. It's just the cross turning the other way around. Okay, and then this curve, I think we saw it a few times already, right? This curve here. This curve is a little bit different. Oh, this curve is a little bit different here. Y square minus x cubed plus y square. I think it's this part plus a dot here. Okay. And then after blow up, what do you think? This one a bit hard to imagine. Actually, this point gets split into 2 points here after blowing up. One, do the calculation. Yeah, yeah. Do a calculation. Yeah, you will see two pre-match here. Okay. Yeah. So basically, you need to throw in your zero set, right? Sorry. Yeah, your your function here, defining function here, and then back compare with these x, y minus wait, what are we doing here? So what's the blow up of this guy? X of t0 minus y times t. Sorry, okay, we just need to solve it like this. So you need to combine these two. Okay, and then see that actually there are two pre-match at 0. Okay. Yeah, you need to do the calculation. See if they calculate it or not for you. Yeah, so you see, they do this calculation here. Okay, so they're throwing, you see, they're throwing this point and this blow up equation together. Okay, you go through the calculation and see that, oh, there are two possibilities. Okay, make sense? It's like what we do last time, right? Last time we have this curve here. Okay, this curve also gets split into two parts. Okay, yeah. Okay, just go and do the algebra. Okay. And then, so you see, in this graph here, say you can see here that this blow up actually is not irreducible, right? It's not irreducible because it's 3-part here. Okay. So we don't claim that the blow up of a variety must be irreducible. It become not irreducible. Well, this is a R point, but anyway, let's see. Right. Okay, and then you have a different blowing up here. So this is y squared minus s cubed. Okay. Remember last time we have a parameterization of t cubed t squared. Okay, this curve here. Okay, also you can blow it up. Okay. Yeah, so this is a two-dimensional blowout, right? See this kind of diagram last time we do together. There's another kind of blow up. So you see this surface blow up here. Okay. So you could start with this surface, a cone. Okay, you blow it up and then you blow it up again. Then get a closed cylinder. Yeah, something like that. Okay. Okay, so how about we get Chiwi to come and do one example? Hi Chiwi，不要浪费时间。哎，这么见不得人呐、是要把我当马赛克？好，我帮你遮起来。在这，对，遮了吗？还谁啊？哎，画不出来。哎，传来，传来。哦，OK，从后面 OK。半个钟啊？半个钟？这个东西5分钟就可以了。OK，好。啊，不要吃你太多时间。OK。不要讲太快了。要问这样。OK 咯，OK 咯。OK，thanks。Doctor Key said invite me to
How about an example of blowout? Uh, one example or two example. Depends on time. Okay lah. Uh, maybe we can start from an easier example. Okay. Okay. For example, we can start from the curve, the zero set of the curve line. Example. Consider. 嗯，哪个荧光？白色过后的颜色，这个
用这一色的颜色，
哦，这一色
不然那个看不懂。
哦，OK。Example. Okay, maybe we consider the polynomial like fxy equals to y square minus x power 5. Okay. Uh, actually, do you know how to verify which point is a singular point? First, we recall the definition lah. But the definition I use here is another one. Here's the definitions. For example, let x be an affine variety. Okay, and then we have several polynomial. For example, f1 to ft defines the define x. Okay, and then of course here we need to let our dimension of the variety to be r, and then this is in akn. Then the rank of the Jacobson matrix is partial f1 partial x1, okay, partial f1 partial x2 until partial f1 partial f1 partial xn, and then here is partial t partial x1 partial ft partial x2 and partial ft partial xn. Okay, and if let's say here is j p, it's got p, point p, point p, point p, point p, point p, point p, and then p is a point in the variety. So if the jp is equals to the n minus r, the n is the dimension of the affine space and the r is the dimension of the affine variety, then we can say p is a non-singular point. And of course, if the jp is not equals to n minus r, then it is a singular point. Otherwise, it is p is singular point. It is singular point. Okay, and then from this example, okay, if we consider the zero set of the y squared minus x power 5, okay, then this variety is defined by this polynomial. So if we calculate the Jacobson matrix, okay, there are two variables. So first, we can try to calculate the partial derivative respect to x. So in this case, our partial derivative respect to x is negative 5x power 4. And then the partial derivative respect to y is 2y. Of course, this is the single polynomial. So the matrix is 1 times 2. And then what is your n? Your n is 2. And then the dimension of the curve is 1. So your r is 1. So your n minus r is equals to 1. Sorry. N minus r equals to 1. And then what point you try to substitute, you get the rank is other than 1. 0, right? If you sub other point, then you get you will get your rank is 1. But if you sub the origin, if the point is 0, 0, then the JP is 0, which is not equals to 1. So this means our point P origin is a singular point. It's a singular point. So now we have a singular point. Then how do we resolve this singular point? Actually, we can use the blow up, the method of blow up. So how do we calculate the blow up? Okay. 颜色笔上面的那个 current template 对 OK 听到了 OK how do we calculate it? We know that the blowout has a definition but of course now we calculate in A2 lah. So we have the equation like first we have a point let xy is a point in A2, and then let's say we have another point homogeneous coordinate which is uv. This is inside pk1, and then it has to be satisfied the equation like vy equals to xu. Am I right? No. Terbalik lah. Definitions are. What's the definitions? Definition should be x. What? If this is u, this is v, then the equation should satisfy y or xv. Okay, xv equals to yu. Okay. But then because this is a homogeneous coordinate, so of course without loss of generality you can assume one of either u or v is non-zero. So maybe we can assume that the loss of generality, assume u is non-zero. But for simplicity, you can actually assume u equals to 1. So now we have y equals to xv. And then just now our equation is fxy, sorry, is y squared equals x power 5. So we try to substitute to this equation, get x squared v squared minus x power 5 equals 0. So you can factor out x squared times the v squared minus x cubed equals 0. Now we have two irreducible polynomial, and then in this case, either our x squared equals 0 or our v squared minus x cubed equals v squared minus x cubed equals 0. And then this actually is x equals 0. And this x equals 0, it defines the exceptional divisor. Exceptional divisor. Actually, you can see if you're trying to substitute x equals 0, then x equals 0, that's our y equals 0, right? And then so you can see your coordinate is like this. This is 1, this is v. This is inside the a k2 times p k1. This is the point. This is the whole point you obtain in this product space, and then you can actually knowing that this is isomorphic to the p k1, which is your e. And then we look at another. This is actually defines strict transform. Strict transform. We denote this is S tilde. And then now you look at the strict transform. Is it smooth? No, right? If you're not sure whether this is smooth, then you can actually trying to use the definition to verify which one is a singular point. Okay, actually there are two equations. Y equals to x v, and these two equations defines the strict transform. So now, if in order to verify whether this strict transform is smooth, you can use the you can calculate the Jacobian matrix again. Now you have a polynomial like gxy equals to y minus xv, and then hash xy equals should be three variable y minus xv, and then h xyv equals to b squared minus x cubed. And then the Jacobian matrix, for example, we can calculate partial g, partial x, partial g, partial y, partial g, partial v, and partial h, partial x, partial x, partial y, partial h, partial v. Then this is just a calculus. This one equals to negative v, and this one is 1. This one is negative x. And then partial x is negative 3x squared. Partial h, partial y is 0. And then this is 2v. And then now we have a Jacobian matrix, and then now we look at now we need to calculate the n minus r. What is our n minus r? Our n is the dimension of the space that we need to deal with. Now in this case, our space is inside the ak squared times pk1. So the dimension should be the dimension should be 3. 3, right? Here already. It's 2 or 3.
You take the product, you just add the dimension. Dimension of AN is n, dimension of PN is 1.
So just plus together. Anyway, the dimension of n is 3 minus R should be what? R should be the dimension of the variety. Means our dimension of the street transform. The dimension of street transform is what? Dimension of street transform is this is still a curve, right? This is still a curve inside the AK2 times PK1, right? So the dimension is nobody answer. No, that's 2. Okay. And then now you look at the what kind of point you try to substitute to the Jacobian matrix, and then you get not equal, you get not equals to 2. When x equals 0 and v equals 0, then the matrix has rank 1, which is not equal to 2. So once again, then you can know that our singular point is again the it's again origin xv 0 0 a, but then wait what am I doing? Should be 0 0 0. Yes. And then another point is x and v equals 0 should be at this point. V is 0, x is 0, y is 0, and then 0, and then here is 1. The singular point is this point, because when x and v are 0, then the rank of the Jacobian matrix is not equal to 2. And then at the same time, if your x equals 0, then your y also is equal to 0. So the singular point is this point, 0 0 1 0. Okay, and then now you can see that even you're applying the blowing out one time, you still cannot guarantee that your street transform is smooth. So you need to blow out again. You need to blow out again. But of course, if you try to blow out again, it suffices to look at this equation. So of course, I to avoid the abuse notation, I reuse the notation like fxy equals to y squared minus x cubed. Yes. And then we know that the singular point is at the origin. At origin. And then you try to blow it out again, then y equals xv. Then x squared v squared minus x cubed equals 0. Then x squared factor out, v squared minus x equals 0. And then either x equals 0 or v squared minus x equals 0. And then this defines the exceptional divisor. And then again, this defines the street transform with the y equals xv. And then now we apply blow up 2 times already. Then you look at, then we can, now we need to check the whether this time our street transform is whether it's smooth or not. So once again, let's say gxy is y minus xv. Hxy equals to v squared minus x. And then, okay, now partial g, partial x, partial g, partial y, partial g, partial v, partial h, partial x, partial h, partial y, partial h, partial v. Now this one is -1, sorry, negative v. Then this is 1, this is negative x, this is -1, this is 0, and this is 2v. Now, no matter what point you try to substitute for the x and v, you will get you will get our rank of the Jacobian matrix 2. So the rank of the JP equals to, no, even you try to substitute back the origin, you still get the your rank of the matrix also get 2. And then as this is exactly n minus r. And then now we we can conclude that our this is what we call minima blowout is true. The minima blowout means that it's the minima numbers that you apply the blowout to obtain a smooth street transform. So in this for this case, our minima blowout is 2. Okay, and then what if I still got a bit time? Okay, so actually, if you're trying to generalize the equation of the curve in this way, like fxy equals to yp plus sq lah, and then your p is between the 1 and q. Of course, your p has to be larger than 1, otherwise your curve is smooth. Okay, and then if our p is divide q, then the minima blowout, let's say m, actually is q divides p only. And then if your q is 1 mod p, then your minima block is Q minus 1 over P. And then if Q is K mod P, of course for some K is between the 1 and P, then the minima block is Q minus 1 over P, but then you need to plus 1. You can check the third case using this example. For example, yq minus x power 5. If you try to blowing up the street transform, you will get y cubed minus x squared. And then this is still got singular point, which is at the origin. So once again, you need to apply one more time. You will get, if no mistaken, should be should be
Q minus Q minus K.
Q. Oh, sorry. Yes, Q minus K. Yes, Q minus K. This time your street transform should be V cube minus 1. Am I right? X. Yes, x V cube minus 1. No, you only can factor out the x squared like if you're trying to substitute y equals xv one more time. And then you only can factor out the x squared, and then the remaining is x v cube minus 1. No. Here is different, right? Now it's y cube minus x power 5. So in if you apply one time of blowing up, you get the y cube minus x squared, this street transform. Actually, this is not smooth. You can check by the definition. So because this is not smooth, so you apply blowing up one more time, you will get another equation of the street transform. And then you can try to check that using a definition, and then it's actually smooth. But then don't try to substitute the origin because this equation is not defined at the origin. So of course you can see if you're trying to like now in our case Q is 5, and then of course this is 2 mod 3. Okay, so here our minima block is 2. So if you're trying to check this result, you get 5 minus 2 divided 3 plus 1 also equals 2. Just using an example to check whether this result is true or not. Okay, I think it's okay.
Okay, thank you, Chiwi. Okay, something I want to comment here. You see, if I remove all these exceptional divisor, street transformer, everything here, this is not high school stuff only. Isn't just high school stuff? Go and find me the x and y, v, right? So this is a different way to interpret new result from all calculation. Okay, and then actually I have another thing for Qi. So you computed your singularity in A kind of A3 or A2 cross P1. Why not you blow up there? Why you blow back your A2? What's the theory there?
Singularity theory. It's a theory say that you can just blowing out the equation without the without the y equals to sv.
So what's the theory? No theorem.
a theorem, but I forgot already.
Okay, I think I need to take it out also because I also need that result. Another thing he mentioned was when he tried to compute this dimension, right? This is the dimension of dimension of A2 cross P1, right? Okay. Actually, I proved in the I think last week lecture notes. Okay, I proved that the dimension of product variety is the product. No, is the sum of dimension. Okay, so now the question is how we compute dimension for AN and PN. Okay, I will do that in the tutorial, but the result is just N. Okay, then you get this number here. Make sense or not? Okay. And then yeah, so this part also I'm curious about why can just blow up like that. I'll try and dig it out the theorem and then I'll show it to you in the tutorial or I'll make it into your assignment. See how it goes. Okay. I think any question? Any question on the calculation here? I think so far, other than that, I'm happy with this calculation. You have any question on this calculation? Any question? So another comment I want to make here is this bit here. This bit here is what we can find using our the IF that we used yesterday. You still remember the IF? You look at because you see at this chart, where is this chart? This is the U0 chart here. Okay. So you can use the formula that we introduced yesterday to find this bit here. Okay, so for example, what's this equation? Okay, equation here, right? Okay, so if you put x 5 and then minus sorry, okay, let's do it this way. So make it into y square minus x to the 5 equals 0. And then if you sub x naught in, okay, for the x component, okay, let's just do x and then sub t x into the y component here. What do you get here? You literally get you get t square x square minus x to the 5. But what is the thing you can divide by here? What is the IF? The maximal x you can take out. Okay, so the maximal x you can take out here is x squared. So you get t squared minus x cubed here. So that's how you get this. Okay, why you take out this x squared here? In particular is what Chiwi say here. If you look at the zero set of x squared, it's actually covered by the exceptional divisor already. Okay. So yesterday, still remember? Okay, maybe I show you this isomorphism that I proved to you yesterday. Yeah, this bit here. So how do you find the blow up in different chart? Okay, in the x is not chart, xi chart. Okay, so what's this j here? Okay, this j comes from this if. Okay, what's this if? This is the maximal integer that divide the power of x naught. Okay, maximal power of x naught that divide this point. Okay. Okay. Any other question? I think this is so far what I can see. Oh, another thing about this definition here. This definition is a bit different from what we introduced. Because if you notice, this definition relies on you need to know the dimension of your variety first. Only then you can find your smooth point. But last time is even general, right? We define dimension of x as the minimum dimension of all the point. Minimum dimension minimum dimension of tangent space. How to find? Actually, if it's kind of singular, you don't need to care because it's very big. So actually, you need to find where is your smooth point. But last time we proved that smooth point is open and dense set. Actually, almost all points are dense, open. Okay. So I will include this into your tutorial also. Okay. Yeah, either tutorial or assignment. I'm trying to organize tutorial sheets and then a final assignment for you from from Smooth Point chapter. I'm writing divisor lecture notes here. Hopefully can finish earlier so that we know where we are heading. So for now, the plan for divisor is we have to prove the Zoot theorem, Riemann-Roch theorem. And then I found something very interesting, amper divisor. I think I want to include that in as well. Amper, yeah, amper divisor. Yeah, but to do this, there's some very technical lemma, which I think we will skip in this class. I'll just tell you that this happened and then it gets us the important result. Okay, actually, the important theorem is pretty easy to prove once we solve this lemma. So meaning we hide the technical part. Yeah, we hide the technical part. Those technical parts is quite studious. It's like how you see how the Noether normalization theorem is very big theorem. I think there's a lot of details inside it. So the details in mathematics usually we split into lemmas. Okay. Okay, let's break for 10 minutes. Let's come back 5:26. Hey, Lydia 他们呢? Where's your group member? You don't know. I text them. So you guys want to meet for 2 hours? I think should be fine. Uh, just meet at my office. 448. 4448. Ah, my office got a whiteboard. Why's your group meet at Monday, Wednesday, right? Jack 你们也是拜三不？拜到晚上。好。 Hello, testing. Okay, so let's do divisor. But for divisors, right, we will just restrict to a smooth projective curve. Okay, so it's a curve in a projective space over an algebraically closed field. And smooth means every point on C has the same dimension with the tangent space. I mean, sorry, with the variety itself. So curve meaning this dimension of this variety is dimension 1. Okay, so you imagine that we are going to use a result from what we know about projective space. For example, the space of regular function O of Pn is constant. Okay. We'll use those kind of result inside this chapter here. So what's the divisor here? Divisor here is pretty simple. So basically, it's just a finite formal sum of points on C. Okay, that's it. Okay, what does it mean by a finite formal sum here? So for any divisor D, okay, given it will be given by the following formula: D equals to N1 P1 plus dot 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 plus Nk. So you kind of attach some multiplicity, okay, to this point here. And then this is a finite sum. Okay, you can pick any point you like, okay, from this curve C here. And then we define the degree. We define the degree of D to be sum of these multiplicity. Okay, so the multiplicity here take numbers in a natural number. So you might imagine that the multiplicity cancel out. Okay, so this is a very general definition of divisor. So this is a finite sum, right? You can imagine that we can add divisor together. You are just adding finite sum together. Okay, you are still a finite sum. So this actually form a group called the divisor group. Okay, so divisor group are all the element D such that D is a divisor. Okay, in particular, this is a abelian group. Okay, because just addition. Really a formal sum here. Doesn't matter we start with what pi here. Okay, in other words, this is a free abelian group generated by the points of C. Generated by the point of C. So this is a group, right? So let's say pi is in here. What's the inverse? Negative pi. Okay, or negative 1 times pi. Okay, negative 1 is a integer. Right. Okay. So this is the free abelian group generated by points of C. Okay, so far? Okay. All right. So obviously, this is not that simple. We need to define some special NI here for things to work. Okay, so maybe we need to look at some motivation here. So let's consider this unique maximal ideal here. So this unique maximal ideal, so I mentioned about unique maximal ideal, right? So this should be something living in a local ring. Okay, so we want to look at it inside this local ring here. So we fix our variety C already. Okay, let's fix a point as well. So this special, I mean, unique maximal ideal here is just the element, the regular function in CP such that GP is 0. Okay. Well, since this is move, okay, since this is move, actually what we see is the dimension of MP over MP square here. Okay, this is the dimension equals to the tangent space, right? Do you remember MP over MP square? Okay, this is a Zariski tangent space. But this space is smooth, meaning what? Dimension of the tangent space or the cotangent space should be equals to the dimension of the variety. But in this case, it's a curve, so this dimension is 1. So you see, this dimension here is a vector space dimension. This is a variety dimension. But vector space dimension 1 means what? How many bases? 1 basis, right? Okay, it's generated by 1 element basis here. So let's suppose that T we take from MP, and if I look it in look at it and in this MP over MP square here, meaning T bar. Okay, if this guy spans the K vector space of MP over MP square, okay, then the claim is, so let me put a big claim here. So then we claim that actually T will generate MP as well. Okay. Okay. It's not too direct, but it's not too hard as well. It's not too direct, but it's not too hard as well. So let's read this statement again. So if I know who generate MP over MP square, I know who generate MP. Okay, so this is the statement we claim now. Okay, so how to prove this? What's the statement you need here, actually? Okay, what's the statement you need here? Okay, so you need a statement that if T will generate MP over MP squared, then T will generate MP. Okay. So let's work backward. See what kind of statement we need. Okay, so let's say MP over MP square will generate by let's say, so in this case we should take what's my ring? OCP. Okay. So OCP, let's say over MP here, we can multiply with plus T. Okay. So can I generate? Okay, can I generate? I generate this vector space. Okay, I want to imply that actually MP is equals to, let's say, OCP times T. Okay. See, is it correct or not? Dimension of K. So after portioning out, this is a few, because this is a local ring, this is a maximum ideal. Yeah, so this field that we refer to actually is this OCP over MP. Okay, so how do we get this? How do we get this statement here? So let's think about it. Okay, So let's say if can we do something like this? So not MP equals to OCP over MPT plus MP squared. Okay, this is okay, right? Something. So in this quotient ring, right, everything like this. So meaning what? Is the element inside MP must be this thing plus something inside the quotient. Okay. So is it possible to go from here up to here? Not. What's the thing you need here? If this equals to this sum here, then we would have this 2 bit the same. Or after multiply, this MP should disappear, right? So multiplying this MP should disappear. Okay. Let's throw it all the way to MP squared then. Okay. Okay. Does it make sense? Because this element's also something in OCP plus MP, right? But MP times T is something live in MP squared. So I can push them into MP squared. Does it make sense? Make sense or not? Because this is a quotient ring, so you are something OCP plus MP. Then if you expand it out, MP times T, because T is living in MP, so this is a thing living in MP squared. So you can push it to MP squared. Okay, so then we are left with this arrow here. Okay, is this true or not? Is this true or not? Is this true or not? How about we write it like this? OCPT equals to MP. Okay, maybe this is not very apparent, so maybe let's move a bit further. So let's say we want to do MP over OCP plus equals to MP over MP over OC. What's this? You got the ideal quotient by another ideal, multiply by an ideal. What if I go a bit further? So how about I write it as rewrite as B equals to MBP. What does this looks like? Ah, Nakayama's lemma. What does Nakayama's lemma tells you? If MP is a proper ideal, then MP times B cannot equals to B if B is non-zero. But now equal means what? B must be 0. Okay. So if you use Nakayama lemma here, you will get that MP over all CPT equals to 0. Okay, which means they are the same. Okay. You quotient it by yourself, you get 0. Okay. Make sense? Okay. So I encourage you to write down the details, but I have more general statement inside the notes. You can look for those. Okay. So we got this. Okay. We claim that T generated MP. So good. We know who generated our MP is just one element here. Okay. Guaranteed by this dimension here. Okay, good. And then next, what we observe is there's a strictly decreasing change we could see here. MP contain MP squared, contain MPK, and so on. Okay. So before strict containment here, are you agree that there's a decreasing chain here? So meaning what? MP, something in MP might not in MP squared. Okay. Yeah. How to get MP squared here? You just take element is an MP and then multiply together, right? But you can do that because it's the ideal. Okay. But something in MP squared might not be in MP. But now here is a strictly containment. Okay, so meaning exactly you cannot find everything in MP squared. Descending chain. Okay, let's see how to prove this. This proof is very important to see the theory later on. Okay, so to see this, suppose that they are equal at some level. Suppose that they are equal to some level. Okay, this basically will solve, yeah, will solve the strictly decreasing if we get a contradiction here. So let's say they are equal at some level. Okay, that means what? Huh? What does this mean here? We know that MP is generated by T. Okay, so this means that there exists G in OCP here, such that T to the power K, okay, equals to G times T to some, let's say K plus 1. Okay, because the two sets are equal. Okay, the two sets are equal, and then we know that T generate TP here. Okay, we know that everything in MP can be written as something times T. Okay, so then this is also true for all the powers. Okay, because how to get the ideal, you just get T multiplied with that T or something from your bringer to multiply. Okay, so because these are the two set equality, right? Maybe they will be differ by some element. Okay, happy? Okay, so but if you rearrange this, what do you get is TK times 1 minus GT. Okay, but what does this say here? 1 minus GT couldn't be 0, otherwise G is invertible. Okay, so TK must be 0. Okay, but this couldn't happen. Okay, but this couldn't happen because this will contradict the fact that the fact that OCP is living in the case. Okay. So if 1 minus GT is 0, that means T is invertible, but T is not invertible because it lives inside the unique maximum ideal. Then TK must be equal to 0. But this also contradicts the fact that all CP is inside the function field here. Okay. So I mean, if you are a field element, right, you shouldn't be nilpotent. Is it true? Because this field is not okay, well, I mean like this field is algebraically closed, so you got infinite element here. And then yeah, you shouldn't be nilpotent as a field element. I mean like okay, field is integral domain, right? If this equals 0 means what? Integral domain of T have to be equal to 0. You have 0 to generate your MP. How to generate your MP with 0? 0 generates 0. Okay. Makes sense? Does it make sense? Okay, so since field is a integral domain. Okay. And we cannot have this part equal 0 since T is not invertible also. Okay, because we choose T from the maximal ideal. Maximal ideal is the part of the local ring that's not invertible. Okay, if you remember. Outside, everything outside should be invertible. Okay. So that's what makes the ideal unique. Why the maximal ideal is unique. Because if you take a little bit more from the complement of that maximum ideal, it becomes invertible. Okay, so not equal to 0 since T is not invertible. Okay, so cannot happen. Okay, so you must remember the whole theory built up from here. Okay, this chain is strictly decreasing. It's strictly decreasing. You can take power of maximum ideal and then you won't find back your original ideal. Okay? Right. So if you strictly decreasing, right, what could happen if you take the intersection? What do you think? If you take intersection, what could happen of all these sub-module, we call it? What could happen now? What do you think? Disappear. Some MP will survive. Huh? You just get 0 inside here. Okay, only 0 is the thing that inside every ideal. Okay, let's prove this. Very interesting proof also. So let's do it. So let's suppose that alpha is in intersection of k equals to 1 mpk here. Okay, well, let's write down what's the definition of this. So for every k, right, we will have alpha inside mpk. So we could write down how this alpha looks like. Basically, this alpha is just some power of t. Okay, let's call it fkt here. In every k, we have this expression because it lives in every mpk, right? Right, so it's some power of k. Well, I mean, like, let's write down the full form here. Okay, let's write down the full form. Well, let's say for some polynomial fkt in OCPT. Okay, actually we know better than polynomial. It's just some t to some power. Okay, that's what we know. And then okay, so let's write down this form here. So we know exactly how it looks like. So fk should look like gk times tk for some gk inside the ring. Okay, this is the exact form. Not polynomial, it's this exact polynomial here. T to some k, some power. But well, I mean, well, if we consider the ideal generated by all such fk here. Okay, let's say we consider the polynomial generated by all such fk. Okay, we know that what do we know? We know that this OCP attached with T. Okay, this T, what's this T? You still remember what's this T? This T is the one we use to generate MP. Okay. So if we consider this OCP adjoin this T here, first of all, this is Noetherian. Okay, why is it Noetherian? Why is it Noetherian? Because this is so we need to argue why the whole OCP is Noetherian. So this is a adjoining an element, right? So if we want to show that this is Noetherian by Hilbert-Basis theorem, to use Hilbert-Basis theorem, we need to show that the coefficient ring is Noetherian. But OCP, why is it Noetherian? How do you still remember what's the equivalent form of OCP? Is a localization of a coordinate ring. Okay. So localization of coordinate ring that we consider here is Noetherian. Okay, so localization of a Noetherian ring is Noetherian. Okay, yep. Okay, so by localization and Hilbert-Basis theorem, okay, we know that this thing is Noetherian, meaning what? Although we are generating this ideal here using infinitely many FK here, but it is really just generated by finitely many of the polynomial. Maybe few of the power is enough to generate. Okay, this I here. So let's pick them out. So let's say FII, FI2, and FIL. Okay, let's choose them. I don't know which one of them, but choose finally many of them. Then you can do this. Okay, then let's rewrite our alpha because our alpha live in everywhere, right? Okay, so let's rewrite our alpha. So let's say our alpha live in the so there are finally many of them. So let's pick the one further, okay, than this FIL state. Okay, let's look at our alpha and the next ideal. Okay, FK here. So what we do here is actually our alpha can be written as j equals to 1 of I alpha of mu j of Fij. Okay. Because we say that finally many of them would generate this ideal here, but then our alpha is living inside this ideal, so we can write it as a linear combination. But remember how we get this Fij. How do we get this Fk from? It's exactly alpha itself. This is alpha in a different MPK. See? This is how we pick this Fij here, Fk here. This is how alpha sit in different MPK. Do you know Buddha? You know Buddhism or Taoism? If not, maybe you can go into a temple. There's one diva called Guanyin Ma. Guanyin. Guanyin. You don't know, right? Okay, I can tell you. There's one diva called Guanyin. There's a lot type of Guanyin. There's an old hand of Guanyin, 千手 Guanyin. What kind of Guanyin you have? Giving birth one, 送子观音. Yeah. 还有 what kind of 观音? 铁观音? That one is a T. What kind of 观音? Other 观音? There's a lot of 观音. Different type, different form of 观音. Okay, so you see, alpha looks different in every MPK. Okay, but all of them refer to the same alpha. Okay, so this is the magic they play here. Okay. But where this mi come from? Mi is just some coefficient in the ring, so okay. But in particular, we don't simply pick this mi. This mi here, to be precise, they are living in MP of IL plus 1 minus L. Okay, because why? We need to make sure that the both sides the T mesh up. The number of T mesh up. Because you need to remember, you live in MPK, right? The exact form of Fi is what? Is T to the power K. So if I say that alpha live inside MP of IL plus 1, right? It should be in some form of T to the IL plus 1. But previously, you need to fill up all these I. Okay, so to make sure that this whole term here also live inside MPIL plus 1. So power need to match up. Okay. Yeah. Okay. So, but anyway, if you live in here, well, we know that all these power of MP live in MP, so it's the right place to get the coefficient. So then let's say we call the whole sum here, because we can do distribution. Let's collect this sum together, IL here, MJ is living in MP. And then we have what? So if we do factorization here, or the distribution, what we get here is alpha times 1 minus mu here, the big sum here equals 0. Okay, the big sum here equals 0. But we know that this have to be equal to 0, meaning both of them either 1 to be 0, right? Note that 1 minus mu evaluated at P is 1, okay, which is not 0. Okay, why? Because mu P live in MP. This is what we show here. Mu P live in MP, but what are the elements inside MP? All the G in OCP in the local ring such that GP equals to 0. Okay, so mu P is 0, so you left with 1P. 1P is 1. Okay, so this is non-zero here, meaning what? Okay, just now what did I say? Outside the maximum ideal, they are all unique. They are all invertible. Okay, so 1 minus mu is a unique in OCP. Okay, so this means what? So this implies that alpha must be 0. Okay, so we prove that alpha is 0. Can follow this proof or not? Okay, if you can follow this proof, I recommend you to, I challenge you, go and read Klaus' proof. See you understand or not. Actually, I spent like an hour understanding what Klaus says. You try and go back and read Klaus' proof. See if you understand or not. Okay, and then you try and compare the version that I already modified. Okay? Yeah. Okay, before we go back, since we have already proved this very important result, I want to give you this definition here. So for every G in OCP, okay, regular at P, so meaning you can write down the fraction form. Then we define the multiplicity of G at P, okay, is given by the following. So now you see I call it multiplicity, so later I will use this to build the divisor. So we call it mu PG. Okay, what is mu PG here? To be the maximum of K such that G is in the K power of MP. From the lemma we proved just now, we can define this, right? This makes sense, right? Because it must stop somewhere. No one lives in all intersection. You must stop somewhere. So this is the number we define for G. Make sense? Okay, make sense? Does it make sense? Does it make sense? Okay. No one can stay forever inside this decreasing change. So you must stop somewhere and then define this the largest number. Okay, so let me quickly make some remark for this definition, then we can finish. So what can you observe from here? So first thing you can observe that a function G will vanish at P if and only if. So GP equals 0. Okay, so you might live inside MP, right? So your multiplicity must be greater or equals to 1. Okay or not? Okay, because just now how we define MP, all the element in the local ring such that GP equals to 0. Okay, so if you vanish at P, meaning GP equals 0, then you must stay at least at MP. Okay, maybe you can stay at further MP, but who cares? Okay, second, if G has multiplicity K at P, okay, what does that mean? That actually means that there exists a ring element, okay, such that HP is not 0, and then we actually have that G can be written as the hash times sum T to the K. If HP equals 0, then this part will live inside MP already. And yeah, living inside MP, then you can push it in. You can always push something in MP into this factory. Because just now, very nice thing is we proved that T will generate this MP. Right? How we find this T here? That's the thing that survived under MP over MP squared. Okay. Make sense? Hey, this is familiar or not? For those who taken complex analysis, familiar or not? No, man. Don't know. Go back and dig your complex analysis. Something about your zeros and posting. Your pole, your zero, go and take it up. Yeah. I think the next class we will try to mention Cauchy integral theorem. Yeah. Try go and dig your complex analysis. Okay. All right. So we have group meeting for this week. So make sure you come. We have Wednesday, Thursday, and then the other group on next Friday, Monday. Okay. So we'll see you next week.